G'day guys. I think I should call this video going back to basics, because that's what I've had to do. Okay. On my previous videos, or one of my previous videos to do with the 7000, might be 2 or 3 videos back, I was showing the onboard switch mode power supplies in the detector, and I was just showing the amount of noise coming out of those particular parts of the circuit, mainly around the inductors and the small transformer. And at the time when I was doing work with the the input module, I thought to myself, well, I won't worry about that noise, because it's not going to get in, because there was no well, was there or wasn't there? I'm going to be careful how I phrase this. There's no obvious indication that noise from those power supplies were getting into the receiver section. But I've got to say this carefully, so I'll put it this way. After having a revisit and going back to basics, I have a different opinion. I think there could have been noise getting into the receiver from the power supplies, and I'll explain it. And it's a bit probably tedious to explain, but I'll explain it. I might have to put the camera very, very close so you can actually see the numbers on the oscilloscope. So I've got to kick away this coil assembly stand, which I use for testing, and I'll just pick this up. I'll move it closer, get over all the detectors. I might have to take the camera off the stand, but I have to loosen that too to do this. There's the detector down there. There's my coffee. Where are we? Well, you can't see the detector because the circuit board's behind the coffee. So what I'll do, I'll drink this. Another bit of advice: don't put coffee near circuit boards when you're working on them. Don't be like me, because that is a really dumb thing to do. Because if it tipped over or something like that, that would create a hell of a problem. So the only problem is I've got hardly any bench room in here whatsoever, and it just makes life a little bit difficult. But I'm going to point out a few things. So I'm going to grab that. The phone just about fell out of the holder because I tilted it down, and then I heard this click, click, clicky, click noise, and the phone was just ready to drop out onto the floor. So I've got it here. Actually, if I'm holding the phone, I can revert back to the high resolution camera, I think. Dear me, if I touch that, does it? No, that doesn't do it. I want to bring up a spot for focus. Hang on a second. That? No, that doesn't do it either. Once I have started filming, I can't switch back to the high res camera. Okay. I can't see, there's nothing there to do it. Anyway, I've got to go around this way, and I won't be able to see what I'm doing properly. But have a look on the oscilloscope there, if you can. This is with the detector turned off, and I've got the oscilloscope probe directly onto the input wires on the receive module. And what you can see there is a pretty small baseline, and that's just residual noise from inside the room getting in there. And those flashes, I've got this on running at 50 microseconds per division, and that will cause intermittent scanning of 50 hertz. It's not fast enough to capture it, and you'll just see bursts of 50 hertz jump up every so often, which they're doing. But I'm going to show you something very interesting. When it's going to be interesting doing this by hand, isn't it? When I first started doing this, with the power supplies running the way they were, I had a spurious noise at the input of that module sitting around what was it? 1.87 to 2.2 millivolts. That's what it was. So the level was very a lot higher than what I'm going to show you right now. So what I'm going to do is turn the detector on. Seeing is believing, so we'll just turn him on, and be careful with that coffee because I've still got it there on the table. I don't like doing this by hand. It's very, very difficult. So there's 7000 firing up. Give it a little while to stabilize. And she's on. Okay. Now, one thing I can tell you, the phone's going to make interference, and I'll probably change the coil pickup by moving the coil a little bit as well. And also what I've done is I've got the camera stand near it as well, so it'll probably cause some sort of offset or something, but anyway, it's no big deal. So we were up around 2 just under 2 millivolts. I think the best I got was 1.87 millivolts peak to peak with those power supplies running. Now, well, I don't know if you can see it on this the low res camera, but I've gone in there and I've completely shielded those inductors, and I've done a conductive shield, and I've also done magnetic shielding. And by doing that, as you can see, the detector is running there. I've been able to get the peak-to-peak noise. It's a little bit offset at the moment, but if I got those center cursors that are doing the amplitude in the right spot, it worked out to 0.96 millivolts. So you could say that by doing a magnetic shielding on the detector and getting the power supply noise out of it, that I've halved the noise on the input of that module. And I will add, in my opinion, okay? But that's what I'm seeing. I mean, test instruments aren't going to lie. You know, I've got the I've even got my own switch mode power supply turned off here so you can see the crow better. Well, I'll just lighten that up again. So I've got this fluoro running at the moment. Makes it hard to see the oscilloscope when I've got that on. But if you have a look, I'll get close. Even with the fluoro on now, the noise hasn't come up. So, you know, that would, not actually a fluoro, it's a constant current LED. It just reminds me of a fluoro type bay, but it's LED. And if you have a look there, there's nothing has moved. There's no change. I was to unplug it, and you can see it's having no effect getting into the receiver. There's nothing happening there. But as far as I can tell, the only way I've improved that is by electrically and magnetically shielding the power supplies within the detector. And I'll tell you what, the reason why I did it, right, because when I tried to increase the performance of the detector, now I'm going to put this back in the stand because it's too damn awkward to grab hold of, and I'll put this up so it doesn't fall out, and I'm going to make sure that I don't put this clamp on the buttons of the detector of the phone. God, I've got detectors on the brain. So I'm going to push that in there. It'll stay there, and I'll loosen it. I'll drop it down a bit, and I'll kill the light because I don't need it really. And I'll turn the detector off as well because I don't need that on. And you can see, you watch the noise floor, it'll just drop back to where it was. And you can just observe the 50 hertz banging away on the screen there. It's a pretty strong coffee, this one. Yeah, so what happened is when I went out into the field and done my tests, the detector I modified, even though it was getting a bit more depth and it was working quite well, it was beating the other detector, but it had more noise. And I was thinking about it and saying, well, is it terrestrial like noise from power lines and whatever is around the area? Is it that type of noise, or is it self-generated noise that I've lifted the amplitude of the received signal to a point where it's starting to amplify internal derived noise from its own switch mode supplies? And in my opinion, the answer was that's amplifying its own noise. Now, anything with a switch mode power supply, I used to design switch mode power supplies years ago, and I know that to get EMC compliance, like type approval for spurious emissions, is really, really difficult indeed. And sometimes it would take a complete redesign of a circuit board, different layout, just to get the noise, just things doing what they shouldn't and radiating, and it's a real problem trying to get anything that as a switching supply, have it meet particular requirements so it can be approved for use. And imagine making a metal detector with probably better sensitivity than anything that you probably know of, unless it's a low noise amplifier in a radio telescope or something like that. But these are low frequency, and it's where a lot of the noise is. It's all this low noise. Even the devices, the semiconductors, they suffer from shot noise, thermal noise. Oh, thermal noise not so much, but um, all sorts of things. A lot of devices, you get noise in the junctions, in the PN junctions of semiconductors, and all these things can increase the noise floor of the circuit itself. But on this detector, on the actual, someone sending me a message. We'll ignore that. I think it's spam. Yeah, the receiver in this is really good, but it could be that it's had the gain set so that it wasn't going to pick up its internal noise from its own power supplies, and that could be a limiting factor there. So you get the noise out, and then you can raise the gain more. So when you think about it, that the internal noise, which I'm measuring on the input of the receiver module, is down half of what it was by cleaning up the stray radiation. We'll call it radiation or flux or whatever you want to call it, emission from those inductors. Well, that has to be an improvement. So that's why I've gone back to basics and looked at it from a basic point of view of before doing any amplification inside the detector, get the noise out of the system. Just do whatever it takes to get the noise down as low as possible. Now, I tried lots and lots of approaches trying to get the noise out, and straight magnetic shielding didn't work. Conductive shielding by itself didn't work. Had to do a combination. I had to go and think back to when I used to make switch mode power supplies and how I used to get the noise out. So I've gone back to the techniques I used to use, and yeah, they work really well. There's even small inductors in there that are just smoothing inductors that are radiating a bit of noise. I don't know if it's very hard to tell if it goes all the way back into the receive module, but by just probing around the receive module itself with a loop on the oscilloscope, I can't pick up any noise now. Before, there was a slight rise in the noise floor. So it's going to be interesting, isn't it? Might be able to get a lot more out of it yet. I will show you, actually. Why not? I'll turn the detector on and I'll set this up. I'll unclip it and I'll show you as a loop. I think if you go back to the other videos, you can tell how much noise was being generated just when I was using the loop. Oh, dear me. This is so difficult. Sitting in front of a workbench with no room and trying to get a tripod in there as well and try and not put it near the coil. Okay. Let's see how it... bloody angle and a half, isn't it? You can probably see that. No, got to keep drinking this coffee. It'll probably go cold on me. But as you see on the oscilloscope, we've got it set at 2 millivolts per division, and I will unclip it, and I will get my earth off and hang on a second. I think I disconnected one of the wires there. I'll just check that. I'd better put my light back on, so I'll see what I'm doing. Oh, there we go. I did. When I pulled the thing off, I actually took the wire out. I had everything turned off too. So bear with me while I do a quick repair. Okay, we'll go down there and you can have a look at what I'm doing. Dear me. Yeah, I did. I just tack soldered it because I was putting the wire on and off with different interfaces there, and get some solder. Get the soldering up the temperature close enough, I think. It's caught around something there, no big deal. I've got to get, come on. Oh, God. Is it on? Yes, it is. It's taking a while to heat up and get the heat to the tip. Now, everyone's using these type of soldering irons now. These are, I don't know, 100 different brands out of China. I'll tell you something too, you can't interchange the elements if they ever burn out with one that looks the same. They're all wired differently, and you end up putting the temperature sensor on the 24 volts and burn that out. So yeah, you can't mix up the elements when you replace them. They're all wired differently by different companies. There's no set way of doing it. Okay, she's on. I'll turn this off again, just so you can see the oscilloscope better. Get rid of some noise. You just see, there we go. Look, I'll clip this on. I'm going to use the clip this time. Not that it's going to make any difference. You can see the noise floor there on the oscilloscope, I take it. That's just a shorted input on a 1-to-1 probe. So I'll turn the detector on. Little green light there, if you can see it. I don't know if you can. I think the battery compartment's in the way. Comes on, flashes, and it actually takes a little bit for this detector to fire up properly. It starts sending a few pulses out, and then when it's settled down, it puts out the rest of them. So, but anyway, we're only looking at noise, okay? Now, those big lines that are poking up there, that's a transmit, right? So that's going to couple no matter what. You can't get around that. But what we're going to do is go look at the noise in between the transmit pulses. What I also want to do there, I just want to see if, usually when I try and do this, it doesn't like triggering it because it doesn't know what it's really looking at. Now I'll just increase the hold off time. Yeah, it wants to get all over the shop. But we're only interested in the baseline there anyway, the actual zero noise. Now, if I've got this up in the air away from it, you can see that on the oscilloscope, the line is very thin and it's baseline noise, I don't know, what is it? It's probably about 0.5 millivolts or so. It's not much. But anyway, we'll go back to these power supplies. Now we'll go to the one near the transmitter, right? Now you see there's an extra spike there from that. That's okay. It's not in the receive window. But if you look at the baseline noise, even though it's jiggling around like a mad thing there, hang on a second. I'll just try and stop that carrying on like a all over the place. I had this set up in a particular way to lock on. Here we go. So you can see that spike coming up behind the transmit. It's no big deal. But if we go over to here, to where it's actually generated from, right? That's where it's generated from, where I've got it over the top of that inductor there. And the noise is far less than what it was before. Even that spike from this power supply area is way down to where it was. But that's not the one I'm really worried about. The one I'm worried about is the one over here, right? And this runs continuously and can be a source of wideband noise. But if you look here, if you look at the other videos that I did, that noise, the horizontal line there, was nearly filling up the whole screen, if you remember. You got to go back and look at the videos. Now, that's where I've done 2 lots of techniques on getting the noise out there, and it has worked a treat. It really has knocked it down massively. There's another inductor here. That's a little bit harder to shield, but if I was right on that, that would fill the screen up 100%. I can do a bit of work there and knock that out even more. But if you have a look, it's so far back on the circuit board, and it doesn't have much energy in radiating out. It just falls away very, very quickly. But you know, when you look at that, and this one here was heaps worse than that, and that's way down. But as we move away, I'm about halfway between it and the module, and we're around about baseline figures already. So I'll go right hard up on the module there, and you can see that you know, we've got that line from the other switch mode power supply on the other side. It's not in a receive window as far as I can tell, so I'm not really worried about it. And across the receive module, there's nothing around there anymore. It's really, really quiet. And that can be proved easy by doing a direct couple on this wire. I actually had it sitting up in the air acting like an antenna, and it was quiet as a mouse. There was just nothing getting into it. So there's more than likely, in my opinion, that there is a benefit to doing some shielding around some of the power supply in these detectors. So yeah, that's a lot less than what it was. I had it up here, and I was getting massive voltage spikes. We call it flux leakage. They are meant to be shielded inductors, but you know how well shielded they are is, you know, yes, open to anyone else's opinion. But that is important to keep the noise out of the system. It really is. So there's a transmit. Go anywhere near that transmit there, and it just really picks up. That's I don't know if you can see it. I've got the camera on a pretty crappy angle to see what's going on there, haven't I? But you know, I've got to sit here, and I can't put the tripod where I am, so you know, I can drag it. But just give you an idea, I've got this even though the detector's dead quiet, this whole area is full of noise. So we'll get over here, and I'll just make sure I don't drop, the phone doesn't slip out. It can. Okay, there's a coil there. I don't even know if I get enough height doing this, but I'll turn on the little wireless module, and even the oscilloscope. The oscilloscope's own switch mode power supply can make noise, and the coil will pick it up. So, you know, we'll turn on the little WM12, where it is, and listen to all the noise that generates. As you can tell, there's noise in the room. I'll turn off the oscilloscope. I don't know if it makes any difference, but a lot of that noise is just 50 hertz. It's really susceptible to 50 hertz. Another coffee. So I'm going to use a fairly big target inside the room here. I've got my ruler there, and this time I've got a Duracell battery. I'm trying to use common objects, you know, just a 9-volt battery. So if you want to do this experiment yourself, you can, and you get an idea of how well your detector's running. So this is on a gain of 1. It's in high yield, and you know, audio smoothing's turned off. I've turned every other function to the off position if it's got an on or off, and that's basically it. It's nothing special about it. But if I get the old battery here, as I go up higher, I've got to do wider and wider swings. Now, beforehand, I was getting it probably that far above the ruler, and now it's up here. So even though it's getting absolutely hammered with 50 hertz, which happens to be the power line frequency in this neck of the woods, I mean, over in the US it's 60, here it's 50. There's me knocking the camera. So I was just doing arbitrary measurements on particular common, easy to get items, and yeah. it's just so noisy here that in some cases, let's turn that off. In in some cases, reducing the internal noise inside a detector can make the other noise, the other terrestrial noise, a lot louder, because the wideband noise being generated inside the detector has a possibility of desensitizing the receiver. So it's basically, it's not making a tone noise because it's a constant, it's not changing. But what happens if you've got noise poking above that, right? It'll be going a very small whoopity whoop whoop, whatever it does. And if you bring that noise floor down, well, in this case, get rid of the noise on both going positive and negative side on the way it does its transmit waveform, and bring the noise in like so. Well, then it's a slight move that was up here being blocked by noise that you're only getting sort of a small amount. Is now you're getting this, and that's going to make the detector really go a lot crazier in a noisy environment. But out in somewhere where it's quiet and there's no noise or next to no noise, such as out in the goldfields, yeah, it should be a benefit. So if there was no benefit, we'll just be using crap type, 10 nanovolt per hertz noise figure front ends, and wouldn't care less about it. And I know going below those levels, going down to around 1 nanovolt or half, is an increase all the way down. But it becomes, you can't keep going and going lower and lower. You can't get down to 0.1 or something like that. It's not going to work. There's just, the amount of, say you had to, if you got rid of the noise by paralleling matched transistors, you'd have to have so many transistors. You probably have 128 transistors sitting in there or something. And they'd all have small cells of transistors inside of each one of those. So you can end up with hundreds of thousands of transistors, in a block of transistors trying to get the noise out. And then there's other things too. You start having capacitance issues, and that wants to slow the signal down when you're trying to pick up very, very fast transients. So, you got to balance everything. You got to balance, how much money you want to spend, how low a noise you want to get down to, and going below a certain point, is it worthwhile doing that? It just blows the costs out trying to do it. But anyway, this is why this is called Back to Basics. Start at the start. Don't start with your low noise circuitry. Start with the power supply. Power supply is going to govern how well it all works. And if you've got switch modes, my God, I've always thought about metal detectors. I've always thought, the biggest problem. Well, think back to any of the detectors. Even just think back to the old SD-2000 that run the most crudest switch mode in it ever, and the amount of noise those detectors were making just out in the goldfield, it would make a hell of a lot of racket when you listen to the signal. These things are a lot quieter. You can do a lot of digital signal processing and so forth. As this one's got a pretty fast ADC in it too, I've noticed. I looked at some of the chips. So you can do things to get rid of the noise out of these, but I feel sorry for the people designing the input stages on these when what is there, 2 or 3 power supplies sitting in there all doing switch mode, trying to do this, and you're trying to measure tiny little signals, and you got this thing trying to kill it. It's one wants to override the other. So go back to basics, get your power supplies right. Even go to bigger inductor sizes, not values, but inductor sizes with more resistive material on the outside of it, just to absorb stray radiation. And we can, as they say, develop a better mousetrap. But that's where we are with this. So I've gone back into it. I've done the power supplies. I'm going to do a little bit more to it. So this is real. I always call it an eye opener, but it's like a damn engineering challenge. And yeah, get back to grassroots on the whole thing. Look at everything, and then have a go at getting the other parts of it working to see if we get more performance. But you know damn well when you can get the noise out of stuff, then it allows to get more performance. You can't do it with a noisy starting base. You can't do it. It's like trying to hear a whisper in a room with 100 people in there having a conversation. And suddenly you get rid of the 100 people having a conversation. You can hear the whisper. That's how these things work. You're listening for whispers. So you got the sensitivity of these requires very, very fast, well, it's basically signal capture. You can't have a sluggish, damped down, filtered input stage that is going to, ignore a lot of the really, really fast decay transients from targets. Yeah, I'm just trying to say this. People who don't know about electronic stuff can get an understanding. Like a small target doesn't hold much energy when it's energized by the coil. It just goes poof, it's gone. And if you have you're trying to make a input stage and say it's it's got a lot of negative feedback and it's got high frequency roll off stuff like that. This thing might decay on a decay curve like that, and your input stage got to decay out like that. It's not going to pick this up. This is going to just fall off. It's not going to be there anymore. It won't pick it up. So you've got to have everything fast. But when you run things fast, that can also generate noise and allow very, very high frequency noise and harmonics and things from whatever power lines even. Even arcing insulators on power lines generate wideband interference, and the interference on that can go up to megahertz easy. It can go up tens of megahertz. Actually, you can go even further than that. I've had a case where the arcing from insulators were going right through 500 megahertz at one stage because it was desensitizing a receiver on a remote site, and it ended up being one of the insulators. We just walked around the directional antenna on a scanner and just pointed at the pole, and up goes the noise level. So yeah, they come out of a truck and they burst water at it in pulses. So not like you have this stream of water and it hits the insulator, but there's a gap between each pulse of water. Otherwise, it conduct. You get electrocuted. It would go pop, 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 and they'd shoot it, and they blast the. It's just stuff that settles out the atmosphere. It gets wet and maybe a little carbonized, and it starts arcing. So they clean that up, and that fixed that problem. But yeah, the same thing will affect metal detectors, especially these. A lot lower frequency. They are wideband detectors in themselves. Anyway, that's where I'm at the moment. I've gone back to basics. It's actually improved the performance of the detector going back to basics. And now we're going to see if we can build on that, like ice the cake, as to say. Anyway, catch us later. Oh, if it turns off, how's that? It won't turn off. What if we're going to hold it? Interesting. It's done a Larry lockup on me. I can't turn off the recording. Anyway, I'll turn off the power. Catch us.